Okay, organic chemistry round 2. Sorry about that. I had some issues with my pen, and I think now we are back in business. Let's check it. Yes, we are back in business. Okay, so let's go back. We had a little bit of vocab. We were doing a little bit of a review here, and we're talking about this SN2 competition here. When we hit this secondary electrophile, this is a much slower reaction. This is where competition starts to happen. So our SN2 reaction is actually in a competition with an E2 reaction. Now, it's two different things, but as soon as we draw the mechanism, we're going to see exactly where that competition can happen. So I'm going to redraw. And I want to draw the mechanism for the E2. And then we're going to look at that competition. Okay, so in order for this reaction to happen, what turns out for an E2 is that we're going to start with exactly the same vocab. Where do we have available electrons? We have them right here with this sodium hydroxide. Look at that negative sign. You have available electrons right here. Here is our leaving group. That means this carbon is the electrophile. So our collision now is what's different. Okay, this is so exciting. I'm going to scroll back up in just a second. But what actually happens in an elimination reaction is that we're going to look at not the carbon that is the electrophile, but we are going to look at what's called a beta. So we're going to call this alpha beta. This is our spacing. We're going to look for a hydrogen that is beta. So in an E2 reaction, we have to add a little bit of vocab. We've got alpha is your electrophile, beta is next door. If you have a beta hydrogen, you can have an elimination as a competition. So why is that a competition, or what does that matter? Well, it's still a collision, but what is the easier collision? There it is. Okay, if you have to collide here in your alpha, remember you have stuff in the way. That's harder. Look at this hydrogen out here, just free and clear. Now that collision is much easier. So this is where the competition happens. They are both second order. They are both a collision, but some of our negatives, some of our available electrons take the easier collision. Okay, now this is where it's a little bit crazy because not all of them. Hang on. This is why we have a second table here. So these are going to choose the easier collision. So if we have a secondary or a tertiary, then these compounds will act as a base. These will always stay, let's spell that right, as nucleophiles. They just prefer nucleophiles, but these versions, O- and N- will act on the easier collision. So let's draw that mechanism. Okay, we have an O- right here. So that means it's going to act as a base. What do bases do? They take a hydrogen. What makes that a base? It is going to bond to the hydrogen, not the carbon. So then what happens? You can't have more than one bond to hydrogen. These electrons have to go somewhere. This is why your spacing matters. This is why this hydrogen has to be beta. These electrons collapse right here. And the only way that happens is they push off your leaving group. Those electrons, when they collapse, what do they form? They form your double bond. That's what makes your pi bond. Okay, then what happened to the OH? The OH has just formed, oh, that's terrible looking. Your OH just formed water. Oh my gosh. And then what happened to your leaving group? We still lost our leaving group as that Cl minus. So here's your leaving group. Now this would be your base turned into its conjugate acid. And here is your elimination. Do you notice you just eliminated a hydrogen and you just eliminated your leaving group? So that's why this is called an E2, elimination, second order. Okay. So an SN2 doesn't work on a tertiary, but an E2 does. So really where we see the actual competition is in our secondary electrophiles. Because in our tertiary, that collision is just too hard here for an SN2. It's just not going to happen. Except now, let's add to our vocab. All right, let's treat that with sodium hydroxide and let's see what happens. Okay, so what are we going to do first? We're going to list out everything just like we did for our SN2. Let's start with our leaving group. Done. That means this carbon is our electrophile and it's tertiary. So right away, you have no SN2. Not going to happen. Here are our available electrons. Look at that minus. What? So now I check my list. Aha. I have a tertiary. So this is going to act as a base. OH, base, tertiary. So if this is a base, that means this will be, whoa, an E2 reaction. So what do I do next? I have to find beta hydrogens. And I'm going to mark this right away as a base, not a nucleophile. So if my electrophile is this carbon, that's alpha. That one's a little hard to read, wasn't it? This is alpha. That means all of these next door neighbors are beta. So let's pick this one. And now let's draw the mechanism. Okay, there you go. Do you notice that all of these arrows flow? All of these happen at once. They are like a cascade of electrons. What is our product then? Okay, we keep the same skeleton. You just made an alkene, and you made it between that alpha and beta, right? You made it between your electrophile carbon and your beta hydrogen. We made water. Doesn't always have to be water. Water just happens to be our conjugate acid. And we made salt. I love it. All right, so this is the main difference between an SN2 and an E2 is that you have a competition in that second order. And the only way you decide is to check out your list. Some compounds will just stay SN2, so it doesn't matter if it's primary or secondary. But our O- and our N-, they tend to then switch to bases for second order or secondary and tertiary. I love it. Okay, so we're going to stop this video now that we've defined our SN2 and our E2. And then our next video, we're going to take just